All right, in this video, we're going to talk about two-sample t-tests. We're moving from having one sample or one group, and now we'll have two samples, two groups. Okay, so in a one-sample t-test, we knew the population mean, but we did not know the population variance. And by extension, we also did not know the population standard deviation. So of course, we had to estimate those parameters from our sample. Now, in most research situations, we have no information regarding population parameters. In other words, we don't know the population mean and we don't know the population variance. So our solution is then to have two groups of research subjects that differ only in terms of manipulation of the independent variable. Now, one of those groups will essentially represent our research hypothesis, what we're really interested in finding out may be true about an experimental manipulation or a treatment or so forth. And usually the other group involves a control condition or some sort of comparison condition that represents an untreated population. So when do we run a two-sample t-test? Well, you have to have two groups or conditions. One group is exposed to one level of the independent variable, and that's often a sample that represents a treated population. And the other group is exposed to another level of the independent variable, and that's often a sample that represents an untreated population. So let's take a look at our amazing statistics selector. So up come the gears. And we'll ask the question, how many samples are there? And at this point now, we have three choices. There could be one sample, there could be two samples, or there could be more than two samples. Now, we've already talked about in other videos what to do, which statistics to select if we have only one sample. And the test that we would run would be either be the z-test for a sample mean or a one sample t-test. And really what it comes down to is whether or not we know the population variance in terms of deciding between those two. Now, we could have more than two samples, in which case we'd run a test called analysis of variance. And there's a bunch of different types of analyses of variance, depending upon our design. But in this case, we're actually talking about currently two samples. And then the question of interest for us is, are the groups independent? And we just need to answer yes or no. And if the answer is yes, then we run an independent groups or independent samples t-test. You'll see it referred to both ways, means the same thing. If the answer is no, then we run what's called a correlated groups t-test, and in some textbooks it'll be called a dependent samples t-test. Now, the difference between the two involves the nature of the samples and whether subjects in the samples have some known relationship to one another. I'll talk more about that in a moment. Now, design notation can be used to quickly and efficiently communicate the type of research design involved in a study. So let me show you how to do that. For example, let's imagine a study in which there's a treatment condition and a control condition. So if we were to use design notation to describe this kind of study and how oftentimes they're done, we might use the letter R to represent random assignment. So for example, for individuals in the treatment condition, after having been selected into the study, and we assume that, hopefully there's been some degree of random sampling, but sometimes that's not the case, then individuals are randomly assigned a condition. And what we mean by randomly assigned is that all members of the study have an equal probability of either being assigned to the treatment condition or to the control condition. If they were assigned to the treatment condition, we would notate that as R sub 1. Okay, so they're in the first group and they were randomly assigned to the first group. So R sub 1 means they were randomly assigned to the treatment condition. Not surprisingly, R sub 2 indicates a random assignment to the control condition. Now, to just keep things kind of simple here, then individuals in the groups are going to either be exposed to the treatment condition or to a non-treatment condition control condition. So if they're in the treatment condition, we note that as an X, right, and X sub 1. So they receive whatever treatment or manipulation of the independent variable that we're interested in studying. Okay, so that's the treatment or the manipulation of the independent variable. That's X for the first group. Now, if we have a control condition in which individuals in that group actually receive nothing, in other words, they don't engage in any other training or manipulation of the independent variable, they're just left to be the way they were when they came into the study, then we don't put anything in that space. So this becomes the no treatment control group type of condition. And usually this is the group that will stand in or represent an untreated population. So because we don't know the parameters in the population of the untreated folks, we need to have a group or a sample that represents them. And then we have to do some kind of measurement, right? And we use the letter O for outcome to represent outcome measurement, in this case, scores for group 1 on the dependent measure. And then, of course, O2 would be outcome measure or scores for group 2, the control group, on the dependent measure. Okay, so the notation communicates really quickly what kind of experimental design we're dealing with. And in this case, we could even give it a name based on what we see in the notation. We would call that a randomized controlled post-test only design. And the blue highlighted area represents where the statistical test will actually take place, because we'll be looking for mean differences between the two groups on the outcome measures. So the mean for O1 versus the mean for O2, that's what we're going to test. Are those means statistically significantly different from one another? Okay, so let's talk a little bit about some design considerations in studies that utilize independent groups t-tests. First of all, the dependent variable has to be quantified, right? We have to be able to attach numbers to it. And it's not just that. The quantification must be on or approximate an interval scale of measurement. So a lot of measures are like this, and even though there's debate, for example, whether or not Likert scales of measurement are truly interval scale or whether they're ordinal, typically speaking, we assume that they approximate interval scale of measurement and then justify running t-tests, even though there is some debate about that. The independent variable is between subjects, and what that means is that participants in the experiment can only be exposed to one level or manipulation of the independent variable. They can't be exposed to both. And the independent variable has only two levels. In other words, there's really, a manipulation of the independent variable versus maybe having nothing occur for the individual. So maybe one group receives the treatment and the other group receives non-treatment. Now, it doesn't have to be non-treatment. For example, it could be treatment as usual. But the point is that there's only two levels of manipulation here. I mean, you can either have one or the other if you're assigned to a group within the study. The treatment group then is often referred to as the experimental condition, and it represents essentially the research hypothesis, what we're interested in. And then the non-treatment group is the control condition, or the folks who have been left untreated. And the other thing is that the participants in the study have no known relationship to one another. And this is often accomplished by randomly assigning individuals to conditions. Now, in terms of some of the statistical assumptions, we assume that scores are independent of each other. Okay, so in other words, a score that you observe on an outcome measure for one participant should have no bearing or relationship to any other scores gained from any other participant in the study. The samples are randomly selected from the larger population. And this is kind of a tough one, because a lot of times we have constraints. There may be a larger population we would like to generalize back to, but the reality is that not all members of that population have an equal probability of being included in the study. So this is something that it's an assumption that often isn't met, but generally it's not viewed as a horrendously bad violation, simply because further replication studies will be done if something important is found to confirm any effect that is discovered in the research. And scores in the population are normally distributed. Okay, and even if they're not normally distributed, again, remember that the sampling distribution, as n increases, will be normally distributed as n gets larger and approaches infinity, and we know that from the central limit theorem. So scores in the two populations have equal variances. Now this is what we call the homogeneity of variance assumption, and it's actually tested when we run our statistics, for example, in JASP or in SPSS. Okay, if we were to just look at the notation, basically what we're saying is in the population, for the groups represented by our treatment group and our control group, for example, that the variances, sigma squared, for group 1 and group 2 would be equal. The test that is typically run to test this is called Levene's test of homogeneity of variance. And typically what we want to find when we run that test is a non-significant test result, right? Because a non-significant result suggests that there is no evidence that the two variances are reliably different from one another. And you might be wondering, well, why is it important that the variances be equal? And we'll be going into this in another video, but the short answer is that as we do the computations for an independent group's t-test, what we'll need to do is pool the variances together, because we have no reason to assume that one variance estimate is better than another, right? We might say, well, you know, if degrees of freedom are larger in one group than another, we should assume that maybe that group has the better variance estimate. But typically the way the test is run is to pool the variance to estimate in the population the amount of spread in the scores. Okay, steps for running an independent groups t-test are very similar to what we did for one sample t-test, and we'll be going through these steps prior to running tests in the future so that you can see that there's a consistent way to go about running statistical tests. So we're going to ask a testable research question. We're going to define the population, and then we're going to choose the correct statistical test. In this case, it's an independent groups t-test. So we know we have two groups. Then we're going to decide, hey, do we want to run a one-tailed directional test or a two-tailed non-directional test of significance? And if it's one-tailed, we have to justify that. There has to be some really good evidence that the effect can only go in one direction. Then we're going to specify the null and alternative hypotheses, and we're going to select alpha, the size of the critical region or the region of rejection. Usually it's 0.05. Then we're going to use a t-table to look up the critical values for rejecting the null hypothesis. This is the threshold that we need to pass for a sample mean to fall far enough into the critical region to reject the null hypothesis. Then we're going to collect our data, right? So we do all this before we ever collect data, right? This is just setting up the test. So then we collect our data, we run the statistical test, and we look at the p-value that's obtained and the which results from the t-ratio, and we look at that and we say, hey, did it fall in the region of rejection? So we make a decision regarding the null hypothesis, and if the null hypothesis is rejected, then we calculate what's called effect size. I'll be showing you how to do that, and conduct any additional post hoc tests. Now, post hoc tests are only run when you have more than two samples. So with the t-test, because you only have two, you don't run additional post hoc tests. And then finally, the last phase is that we then generalize back to our population, to kind of think about our results and then revise subsequent hypotheses. Okay, so let's take a look at the big picture. The two sample t-tests are run when there are two groups or conditions. And there's really two types of these t-tests. One is an independent groups or samples t-test. It's called either one. You'll see it both ways in textbooks. And that's used when there's no relationship between participants in the two groups. Now, a correlated groups, also called a dependent samples t-test, is used when there is some known relationship between subjects in the two groups. Now, in terms of assumptions, the independent groups t-test assumes that the data, the raw score distribution, is normally distributed, although there can be violations of that, and the t-test is pretty robust against that violation. Homogeneity of variance exists between the two groups. They have equal variances in the population. The groups themselves are independent and the scores are independent. So any given score should not depend on any other score in the data set. And then finally, we have measurement that approximates interval level measurement. Okay, and so in our next video, we're going to be moving on and we'll be talking about how to actually compute the independent groups or independent samples t-test.